On behalf of the Department of Applied Physics and Informatics and Keio Global Research Institute, I will introduce the Dr. Jason Potticary from University of Bristol. And shortly, can I introduce you? Shortly. He was a PhD candidate in 2014. And he do something like an internship in my laboratory. He tried to make inorganic materials with arsenic, untoxic one. And after that, he returned to the University of Bristol and he obtained a PhD in 2017. And now he is a research associate in University of Bristol and Department of Chemistry. And in 2016, he make a very exciting work. I think he will talk on the later. Yeah, I think it is somewhat difficult for us, including me. the very state-of-art technology. But it's very exciting and interesting from a viewpoint of industrials and pharmacy and electronics. And as many were, I think, roughly energy areas. So, so in this chance, I have a chance in this seminar. I invite him for the whole seminar for you, and it's my pleasure introduce Jason Potticary, Dr. Jason Potticary, to you. And yes, please start your presentation.
Okay, hello. First of all, I will preface this talk by saying I don't know how much you do or do not know about molecular crystals, so I will start fairly basic, and I apologize if I'm going over material that you've already learnt and you already know about. So first of all, just a bit of background. I'm at the University of Bristol, which is right here, where Wales meets the south of Wales meets England, and there is a large estuary called the Severn Estuary up here, which is very tidal. So in Bristol on the coast, we have the largest tidal flow of anywhere in the world, I think 11 meters between high tide and low tide, which means when it's high tide, the sea is right up to the sea barrier. At low tide, you can't see it. It disappears into the horizon. Bristol, also famous for the Clifton Suspension Bridge here, designed by Brunel. He died before it was finished, but it still has about 25,000 vehicles go over it each day. These rows of houses are quite iconic of Bristol. Here you'll see them all over. We have a lot of hills, not big ones, but small hills. But there are many of them, and they're very steep. And we often have this kind of terraced, coloured block throughout. This is the Wills Memorial Building at the top. It's not a cathedral. It's part of the university. It's where we graduate at Bristol. And you can see it's, again, on top of a hill. We also like our hot air balloons. In Bristol, we have the second largest balloon fiesta in the world. I think Turkey has one bigger. But every August, about 150, 200 hot air balloons take over and go over the city. And also Banksy is from Bristol. So throughout the city centre, you'll see pieces of artwork that Banksy has done in his time at Bristol. The University of Bristol, it's a top 50 university in the world, top 10 in the UK. 13 Nobel Prize winners are associated with the university. That means either alumni or having taught at the university. Top 5 for research in the UK. 6th in Europe for teaching. And I only learnt this when I was looking up the statistics for this talk, but apparently top 10 for sports in the UK as well. We have quite a lot of students, 27,500, 7,000 of which are postgraduate. In chemistry, where I work, 600 undergraduates, 215 postgraduates. That means doing a master's, a postgraduate master's or a PhD. Background to myself. as was said earlier, I did my undergraduate degree in Liverpool, graduated in 2002. And then I went into industry. I'd had enough of university, went into industry and made microbiological media. That means I made agar for microbes to grow on and eat. We tested food. It wasn't very chemistry, but it was a lab job. After that, I joined a rock band. And this is me here in the green. So I did that for about 4 or 5 years. Then I came back into industry and made binder for insulation. So I don't know what it was like in Japan, but in Europe, at least, all loft insulation used to be this yellow color here on the right. And that's because it was phenolic-based resin binder to hold the glass fibers together. And I was part of a team of 6 that basically helped formulate this brown. They called it Ecos. It's basically a polymerized sugar that's been made to be water resistant. But now in Europe, at least, most insulation will be this brown color, and that's because of the formulation that I was a part of the team. After that, I did a teaching degree and was a high school teacher for a couple of years. Realized after 2 years teaching at high school wasn't really for me. So I had the opportunity to go to Caltech, and I did 6 months in Sorsino Hailey's lab making oxide electrolytes, solid oxide electrolytes for fuel cells, specifically barium zirconate, erbium-doped barium zirconate. While I was there, I applied to do my master's at the University of Bristol under Simon Hall. He was here a few weeks ago. After my master's, as was said before, I went straight on to my PhD, and then in 2014 I came to Keio to work with Kamahara Sensei. I think you can see there and maybe there. He is enjoying some food. And then before the end of my PhD, I was employed as a postdoc to carry on the work that I was doing with my PhD. And I'll just talk quickly about that. The Magnifarm project, which is who employs me, is a project based on novel crystallization means of pharmaceuticals. That is, we're looking at how magnetic fields affect crystallization of pharmaceuticals. Here we have Rui. He works with crystal structure prediction, so he's completely theory. He just works with computers and predicts crystal structures, calculates energies, properties, and whatnot. Sana, in the middle, she's at Nijmegen in the Netherlands. She has access to very, very strong magnets, big facility-sized magnets of about 44 Tesla in the sample space. And Jen is in Limerick in Ireland, and she works with liquid cell TEM, transmission electron microscopy, and also maybe structure solution if we can get that far in the project. So Bristol are tasked with crystal growth and characterization. This is our lab. We have 4 of these big EM7 Lakeshore electromagnets. They go up to about 3 Tesla that are designed exclusively for crystal growth. This is an experiment set up at the bottom here. This is an experiment set up in one of those magnets. We have also a couple of ovens, a DSC, UV-Vis, IR, quite a neat little lab. So, on to molecular solids, which is what I work with almost exclusively. Molecular solids are solids, maybe crystalline, maybe amorphous, that are completely made up of molecules. Here I've just done a cartoon, like a dummy molecule, that typically arrange in a crystalline structure. They can be amorphous, they can be co-crystals. It doesn't have to be one molecule, but keeping it simple, technically, this is what a molecular solid would look like. So if we look at one closely in that arrangement, you start to understand that the bulk properties of the material that the molecular solid makes are a function of how each molecule interacts with its nearest neighbor. So here we can see that the red atom is interacting with the 2 white atoms. So that is going to be the dominant intermolecular force in this crystal. So if those bonds interactions are fairly weak, then we're going to have a very soft material. If they're very polar, if there are induced dipoles there, then maybe it will be very soluble in water. In a very general way, in the hierarchy of bond interactions, we are dealing with effectively those last three, because if we're breaking if we've got ionic bonds, we don't have molecular crystals, we have a salt. If we're breaking covalent bonds, we're changing the molecule. That's not what we want to do. So we're interested in hydrogen bonding, dipole interactions, induced dipole interactions, dispersion forces, that kind of thing. So a quick example. This is just a little paper we've just published about a diiodochalcone. This motif in the middle is a chalcone, and we've got two iodines on each end. Up in the top right, this is a calculated electrostatic potential of that molecule. So effectively, we're looking at how electropositive or electronegative that molecule is at certain regions. And we can see here, sort of around the oxygen, we've got a red zone here, which means we've got a slightly electronegative region, would be expected of oxygen. And then, because of that, we then have this electropositive region in the backside, because it's pulled that electron density over to the oxygen. If we look end-on to these molecules, we can see here, we've got these little blue spots of slightly electropositive region. This is a fairly interesting interaction that is commonly seen in halogens, especially iodine. What's happening is, because iodine is so electron dense, if you attach it to an electron withdrawing group like the aromatic ring, what happens is it pulls that charge away from the iodine enough to expose a little positive region, and that's called a sigma hole. And the reason that's interesting with molecular crystals is because you then have a single atom which is partially electropositive and around the outside partially electronegative. So we don't have the iodines interacting like this, because that's positive and that's positive. What ends up happening is we have this kind of interaction, and that's called a halogen bond. And we have those here, these halogen bonds that go all the way through the crystal and make these nice iodine channels, which we think might be interesting for conductivity. Lots of delocalized charge moving around. But also in this crystal, what we have are the stacking interactions, the pi stacking dispersion forces that are holding the crystal together and stabilizing it in a third dimension. So this is the sort of thing we're dealing with on a daily basis. Polymorphism is really, really where my specialism is. And that is effectively the ability of a molecule to pack in a number of different ways, not just the most efficient, so it's the densest. Any molecular crystal can pack in a number of ways if exposed to the right parameters, the right variables. So, for example, if we environment A, let's say we use physical vapor transport, we get this packing, and if we recrystallize it from ethanol, environment B, we get that kind of packing. Now, what you need to pay attention to with these two polymorphs is, in form 1, we've got the red end pushed up against the green end, so we've got that kind of interaction. In form 2, what we have is each end is pushed against the middle of the molecule, so that interaction is going to differ. So, by changing how these molecules interact, we change the bulk properties of the material. A good example of this is paracetamol, the painkiller. Paracetamol has a number of different known forms. If you dissolve it in ethanol and recrystallize it, which is the standard means in which to crystallize ethanol, this is the type that's found in pills that you would buy in the pharmacy. Gives us the thermodynamically most stable monoclinic form of paracetamol. This is produced on an industrial scale because it's nice and easy to make. However, if you crystallize it from the melt, that is, you just take the molecules as a solid, you melt them and you slowly cool it, you get form 2. Now, the interesting thing about Form 2 is it's metastable, which means at the temperature in which you're measuring, it's not the thermodynamically most stable. Given the chance, given an activation energy barrier, it will transform to the thermodynamically most stable form. However, it does seem to be fairly stable at room temperature, and the reason this is interesting is it's got a higher dissolution rate, which means when it gets to your stomach and hits aqueous acids and water, it dissolves faster and gets into your bloodstream faster, so it's more efficacious. It works better as a painkiller. And it's also more compressible, which means if you're making this on a ton scale, tons and tons at the same time, it's easy to process and press into pellets. However, the trade-off is, do you invest lots of money into heating up lots of paracetamol to melt it, or do you just recrystallize it from ethanol and accept the fact that it's going to be slightly less efficacious? In this case, the heating is too expensive, so Form 1 is always the one seen in tablets. The only time you're going to see it in tablets is if someone comes up with a room temperature, room pressure way to make Form 2 without lots of hassle or toxic chemicals or additives. A very famous case of this is that of ritonavir. Anyone that works in polymorphism or organic pharmaceutical crystal growth would have heard of ritonavir. It's a protease inhibitor that basically stopped people dying from AIDS. So if you look at the dotted black line in this graph, which is the important one, that's the number of deaths from AIDS, the disease. And when ritonavir was released, you see this drastic decline. It went from 50,000 deaths per year to 18,000 deaths per year. So people can then live with AIDS without it being a death sentence. So it was a big thing. Abbott Laboratories made billions off ritonavir. They sold it all over the world. It was a blockbuster. It was changing the world. Then, all of a sudden, it stopped working. People were taking it, and ritonavir just wasn't doing its job anymore. And they initially didn't know why. People were taking it, and it just wasn't doing what they needed it to do. What had actually happened was there was a second form of ritonavir, second polymorph, here, Form 2, that they hadn't found. So all of these pills that they distributed around the world were Form 1. People were taking it, it was dissolving, and the dissolution, it was going into the blood and doing its job. The molecule was fine. However, Form 2 appeared, and all of a sudden, it wouldn't dissolve, because the dissolution, how fast it dissolves, is exclusively a function of the molecular interactions between these molecules. So basically, it had gone to a more thermodynamically stable form that wouldn't dissolve, completely insoluble. So people were taking it, and it was just going straight through the body and being excreted by the kidneys. Through the gastrointestines. Now, the problem with this was, now that Form 2 had appeared, they couldn't make Form 1 again. Literally could not make it again. The factories, they were producing it, they were getting Form 2 every time. They even built brand new factories to try and stop this Form 2 from appearing. It worked for a couple of weeks, and then Form 2 appeared. So globally, all at once, a tiny speck of Form 2 appeared, and it converted the entire supply around the world. Phenomenal. And Abbott Chemicals lost lots of money because other people started developing protease inhibitors that were very similar. Did the same kind of thing. So basically, any property of the bulk material can be changed through polymorphism. Morphology, hardness, color, melting point, conductivity, band gap. Down in the bottom right, there is a picture of chocolate, and you probably see this fairly often in Japan because it gets so warm. If you've ever come across chocolate that looks like this, and you don't quite know what's going on, the cocoa butter in chocolate has a very specific polymorph. the one that they make, the one that you taste, it has a particular taste, a particular texture. If you warm chocolate too much, it changes polymorph, and then it stays that other polymorph, which looks like this. So all this means is that the chocolate has gone over a certain temperature and it won't revert back to the old polymorph. Chocolate companies spend millions and millions developing techniques in which to get their polymorph absolutely spot on for how the chocolate tastes and melts and whatnot in the mouth. Rubrene, a molecular crystal, as far as I'm aware, still has the highest conductivity of any molecular semiconductor. It's used in OLEDs and OFETs, but there are a number of different polymorphs. The orthorhombic form is the most conductive. So luckily, if you're growing rubrene to build devices on semiconductors and whatnot, chances are you'll end up with the orthorhombic form, which is the most thermodynamically stable. But it's worth knowing if you are going to build a transistor or an OLED on an organic crystal, just because you have the right molecule doesn't mean you're going to have the right crystal when you come to building your device on it. Okay, and that's worth remembering with regards to the conductivity of the material you're going to work on. So organic crystal growth is basically a function of making a supersaturated system, be that in solution, be it in physical vapor transport. Typically, a crystallization experiment is you dissolve your solute in a solvent, you then increase the supersaturation. It can be done in a number of ways. You can have an evaporatively driven crystallization where you let the solvent come off bit by bit, and that increases the supersaturation here. So you dissolve more and more and more as temperature increases, and then you filter out any nucleation sites, and then you cool it down, and it won't crystallize straight away. You need that that area of supersaturation. And then when it starts to crystallize here, it will just crystallize and take all the solute out of the solution. You can also do it by cooling, removing the solubility by using an anti-solvent. So you can add an anti-solvent to the system, and that makes the solute less soluble. Physical vapor transport is another one, fairly recent way of crystallizing materials, but then you use a saturated gas to carry the molecule into different temperature zones. Just a quick point on classical nucleation theory, where crystals come from, why they grow. This is just a very basic graph. It's actually based on the formation of water droplets. So there are a lot of assumptions in classical nucleation theory, and for most systems, it seems like this is not actually right, but it was thought of as the gold standard for about 100 years. Basically, the idea is the surface of a particle is an unfavorable environment. The bulk is favorable, energetically speaking. So as our cluster gets bigger, we end up with this, because the surface is reliant on r squared and the volume on r cubed. We have this blue line here, which is a summation of the two. So here we have what's called the critical radius, which means as soon as it gets that size, it becomes more favorable to get bigger than smaller. So when crystals start to grow, they grow. They don't redissolve. But again, like I said, this is a very, very fast and loose description of crystal growth, and in pretty much every case that they've looked into it has been shown not to be true. But it's worth remembering just for when we get onto the growth of crystals in a minute. One other point about enantiotropic and monotropic crystal systems. With polymorphs, you can have different phases appear at different temperatures. So if you cool down pyrene, it's a small 4-ring system. If you cool it down at about 100 Kelvin, the whole system changes to a different polymorph, and then you warm it up again and it changes back to where it was originally. Now that's called an enantiotropic transition. Enantiotropic just means that the most thermodynamically stable changes as a function of temperature. There is a crossover of that energy. So these two dotted lines, if we think that's the energy of polymorph 1 and polymorph 2, we have transition points here and here before it melts. And they don't need to necessarily change polymorph as a function of temperature, but what they do need to do is have that energy difference. One needs to become the most thermodynamically stable. And a monotropic system is where there is no crossover. So one will always be the most thermodynamically stable, regardless of where you are with the temperature. So why grow crystals under magnetic fields, which is what we ended up doing. So typically, growing crystals under magnetic fields makes fewer high-quality crystals. It's been seen throughout the decades. No one really knows what's occurring, what's going on with it. But if you grow proteins or large organic molecules under a magnetic field, what you tend to get is that it produces higher quality crystals. So this is necessary if you're trying to characterize a protein. If you grow it in a crystal, you get complete structure solution, and then you can look at the structure of the protein. You get alignment with the field. So the magnetic susceptibility of a unit cell, a crystal unit cell, is not isotropic, so one will always favor pointing along the field when the cluster gets big enough. And crystal inception time increases. Now what I mean by that is with saturation points, what you end up with is you can make it colder, or you can add more anti-solvent before crystallization begins. But that's the takeaway from these papers. So I thought my beginning of my PhD was to make transistors on a polyaromatic hydrocarbon called coronene. Coronene is this big circular disc-shaped PAH. PH means polyaromatic hydrocarbon. It's very rigid, very planar, has lots of delocalized electrons, and used as a model system back when computers weren't that great to simulate things like graphene, because you've only got a discrete unit of aromatic rings, so it's not very computationally expensive. It's something that you can model properties on without spending lots of computer hours. Typically, coronene grows in these yellow crystals that are up in the top right-hand corner. So I thought I'll put these crystals, grow them in a magnetic field, and what I started getting when I perfected the method was these very large orange crystals. You can see here in the cuvette. It's a very crude setup. Originally, we didn't have these big electromagnets. This is the big brown cylinder is a pole piece from an old vibrating sample magnetometer, VSM, and this is just a neodymium magnet, and they were just being held together by magnetic forces, and the crystal was grown in there. We put that whole thing in an oven with temperature control, and we lowered the temperature very, very slowly, and we ended up with these big orange crystals. The crystal structures of these polyaromatics tend to fall into four groups. This was categorized by two guys, Desiraju and Gavazzotti, back in 1989. They plotted 32 known crystal structures of polyaromatic hydrocarbons, and they plotted the short axis against the nearest neighbor angle. So the shortest axis of the unit cell versus the angle at which these molecules sit relative to each other. And they categorized them basically into beta herringbone, gamma herringbone, herringbone, and sandwich herringbone. So we have A is herringbone, B is gamma herringbone, C is sandwich herringbone, because you have this dimer motif, and D is beta herringbone. But they all tend to adopt these crystal structures based on them being flat, so that the faces can interact, and the sides and the faces can interact, and that's pretty much all you have in these crystals. And coronene sits right there where that green spot is, right there, up in the gamma region. So coronene adopts a gamma herringbone structure. When we did single crystal diffraction on the new orange crystals, what we found was that it had a shorter B-axis, and the angle in which these molecules sat next to each other had changed. So when we plotted that on the graph, we found that we actually had made a new polymorph of coronene here on the in the beta region. So we called it beta coronene. You can see the unit cell parameters down here. The B-axis is significantly shorter. So a polymorph that no one knew existed, we'd found by growing these crystals under magnetic fields. Were we the first to do polymorph selectivity? No, we weren't actually. When we started looking into the literature, there was a group in Holland and there was a group in Japan actually that had done these experiments in the past. This is an isoxazolone dye and this is terpyridine. Both had shown that with ample magnetic field and crystal growth, you could select the polymorph based on the amount of magnetic field. And the reason this was significant is because no one really knows why magnetic fields affect crystal growth. Actually, if I go back to this slide, there is some assumption about, so this experiment up here, they grew I think it was a lysosome crystal in the presence of a magnetic field, and you can see so when solute joins a crystal, you get a depletion zone of solvent without the solute in it. And these convection currents here of solute depleted solvent plume up. That causes concentration gradients, and it's thought that those concentration gradients cause nucleation. By using the magnet, you're getting microgravity, you're suppressing this convection gradient, and you're getting better crystals. However, where we were with this, it looked like we were below the threshold for microgravity to have any real effect. Of the two structures, this is the powder diffraction patterns. The reason I've labeled indexed these particular peaks, they're going to be relevant in a minute, but if you look, if you were to overlay those two patterns, the bottom in the beta pattern, the 101 bar and the 012 peaks would be basically underneath the 101 bar and the 112 reflections of the gamma coronene. So if we were to mix those two patterns, it would be the 002, 101 and the 112 peaks that we would see emerge. Rui at UCL made some calculations on coronene. He did a crystal structure prediction on coronene after we found the second polymorph. So every one of these spots is a new energetic minima for the coronene crystals to sit. So each one of these is a slightly different crystal structure. And you can see at the bottom, gamma and beta are by far the lowest energy. So it makes complete sense that those are the two that we see. Surprisingly, the beta is the lowest energy. These calculations are all done at 0 Kelvin. So it looks like at 0 Kelvin, at lower temperatures, beta coronene is actually the more stable. And this calculation on the right is a phonon calculation to try and simulate temperature and work out where the crossover is. And you can see here, beta is more stable at low temperatures, gamma is more stable at high temperatures, with a crossover at about 330 Kelvin. So can we see that if we lower the temperature? This graph might look a little confusing, but effectively what we have is from left to right, we have a powder diffraction pattern with angles 5 to 35. From the top to the bottom, we have temperature going from 300 to 12 Kelvin and then back up to 300. So we took a powder diffraction pattern every couple of degrees all the way down to 12 Kelvin, and then we brought it back up to 300 and took a powder diffraction pattern every couple of degrees. And you can see, as marked by the blue asterisks, we actually see an emergence of peaks appear. Here and here, slightly different temperatures, but these indexed perfectly to the what I showed you earlier, the 002 and the 101 and the 112 of the beta phase. So it shows that there is a partial conversion of gamma coronene to beta coronene as we lower the temperature. Also, something that was kind of surprising was that they appeared at a lower temperature in which they disappeared by about 100 degrees, which we didn't expect. So there's some kind of structural hysteresis. Initially, we thought, why isn't it all converting like pyrene or DMSO do when you lower the temperature? So I just did an experiment, changed the crystallite size, and then ran 300 Kelvin, 12 Kelvin, 300. So I didn't do the whole temperature scan down, just 3 powder patterns to see if I could change the amount of conversion. And it actually seemed quite easy to do. The smaller crystals that I made, we ended up with a way greater conversion rate from gamma to beta. And the distribution of sizes of those crystals wasn't actually that great. So within that 1.7 to 7.7, somewhere we're going from 4% to 50%. So it does seem like size is a factor. It could be that the methods in which I used to make the crystals increases the number of defects, holes, impurities, but on the face of it, it looks like it's crystallite size that's having an effect. If you take 2 coronene molecules and minimize their energy in a vacuum, you get this overlap here. An offset by 1.59 angstroms. This has been done repeatedly in the literature. I've redone it myself. It always happens this way. This offset is always the way in which coronene sits when you've got 2 molecules together. Even if you calculate a cluster of 3, 4, 5, 10, there's always this offset between neighboring molecules. In gamma coronene, the one that everyone knew about before, what we had was this 3.17 angstrom offset, and it was commented on a number of times, why don't we see the 1.59 offset in coronene crystals when this interaction is so favored energetically? The edge face interactions must really be stabilizing the crystal. But in beta coronene, we actually have a 1.61 angstrom offset, which mirrors the calculations done over the last few decades of these 2 things interacting, which implies that the edge face interactions of these crystals are drastically minimized, which would also justify why that angle is so much less. So another new method that's been developed at UCL, Rui has developed a way to calculate the magnetic susceptibility of a unit cell based on where these molecules are positioned. So what you're looking at here is the ellipsoid that is indicating the magnitude of the anisotropy of the magnetic susceptibility. So if it's here on the single molecule, that means that if you were to put the magnetic field going across the plane of the molecule, it wouldn't be that energetically unfavorable. However, if you turn the magnetic field so it's going through the molecule, suddenly there's a greater susceptibility on that molecule. So what you're seeing here is gamma on the left, beta on the right, and you can see the ellipsoids for beta coronene are a lot greater, implying a greater magnetic susceptibility. So can we see that? In a squid magnetometer, yes we can. So I've clipped the data because the paramagnetic upswing is huge and pushes this into the noise. But we've done this many times at different field strengths, and it seems to scale with field strength. So if you follow the red dots back, there's a kind of corner close to 150 Kelvin, and then it swings upwards. And then on the way back down, there's another corner here at it's about 220 that swings down, and then we end up back where we started when we get to room temperature. So we see a hysteresis in the magnetic susceptibility. Can we match that to the hysteresis we see in the structural analysis with the X-ray diffraction? Yes, we can. So on the right, these points, I've colored them to look the same as the squid data, but basically I've done Rietveld refinement on each of the powder patterns that we generated in that low temperature data. But I've refined it to the gamma coronine structure. So the more we deviate from the gamma coronine structure, the higher the R value is going to be. So I'm not catering for the beta coronine in this analysis, basically to show a deviation away from gamma coronine and try and get some feel for how much we can see this. And you can see the hysteresis follows the squid data almost perfectly. It doesn't quite go as low here, but it's a really, really good comparison between the two. This wasn't exactly the same sample, so the fact that the crossover is in a different place likely just means I had slightly different crystallite sizes. So why is this happening? Why is the magnetic field changing the polymorph? I went over to Nijmegen to use some big magnets to go up to 20 Tesla, and their magnets are big. They look like NMR machines, big drums with hundreds of liters of water per second going through them to stop them from burning out. So this is the sample rod, a schematic of the sample rod. So here's a cuvette with my sample, and I'm basically just bouncing light through it to try and pinpoint the moment of crystallization of the sample. So I'm setting it to a high temperature, turning the magnetic field on, lowering the temperature, and trying to pinpoint the point at which it starts to crystallize. So basically, the lower on the graph the data point, the longer the crystallization has been suppressed. And what we saw originally was this kind of Leonard Jones looking plot, where we have a drastic decrease in crystallization temperature from 40 to 5 degrees over the first Tesla. And then as we push it towards 20 Tesla, it actually comes back and starts crystallizing near to where it started. It never quite reaches back up at 40, but the fact that it came back was very interesting, and there seemed to be two competing effects, and we genuinely have no idea why. The graph on the right is basically just a more detailed look at that area between 0 and 1.5 Tesla, and you can see we get the same inflection point with where the crystallization begins. So can we see this in any other systems? Is it specific to coronine with this large diamagnetic susceptibility? Carbamazepine is, if you worked in pharma, you would recognize this instantly. It's a very, very well-studied drug, especially structurally. It's an anti-epileptic drug, billions of dollars of sales. Has four known native anhydrous forms. There is a fifth one that's grown up epitaxially, but there's basically 4 forms. And this is the CSP here, crystal structure prediction. So each one of these points are a new energy minima for this crystal to exist. And the known forms are circled with blue circles. Form 3 is that red one at the bottom. That's the one we see if we just dissolve it in ethanol and let the ethanol evaporate. And the other forms are found by heating it up, cooling it down, additives, different solvents, that kind of thing. But it's a very well studied drug. So I started looking originally for this little black data point down the bottom, which there's a whole other reason why that's difficult to get, but it seems to be the lowest energy. Why no one's seen it yet is I mean, it makes sense, but I'm not going to go into that here. Anyway, so I did the low temperature powder diffraction on it, again, to see if there was any kind of phase transition from one to the other. And what I see is nothing. There's just expansion, contraction, that's it, no phase transition whatsoever. So am I to expect anything to change with carbamazepine? So back in Bristol, this is where we designed this piece of kit. This is basically a copper block with like a horseshoe-shaped holder. We slot the cuvette in like this. We push it into the copper block. This is a water pipe in. This is a water pipe out. So we flow water through the copper block nice and fast so we can keep the temperature nice and stable. So we use a water heater to control the temperature of the water, and that water then controls the temperature of the copper block. We've also got an optical cable going through the middle, so we can also, again, measure the point of crystallization. But when we put carbamazepine in a cuvette, in the magnet, what do we get? Ooh. What we see is we do get polymorph selectivity. We go from form 3 to form 1. Form 1 is characterized by this fibrous form, long, high aspect ratio needles, and form 3 is characteristic of these rhombohedral block-like crystals are characteristic of form 3. So we get form 3 out of the magnet, form 1 in the magnet. So great, it looks like we've got another system which we have polymorph selectivity. Do we have the undercooling? Initial results would suggest we do. This is a lot messier than the data you saw a minute ago, but this is only between 0 and 2.2 Tesla. And we definitely have that drastic decrease initially, and maybe some kind of upswing as we go to higher fields, but this needs more work, more data needs to be collected. However, as I said, it was a very well-studied material, and what we know about this is that this is a paper published by Parambil, 2017, I think, who basically did a concentration study with carbamazepine and said, the more saturated your carbamazepine solution, the different forms you get. So you get form 3 at low concentrations, form 2 and form 3 concomitantly as you increase the saturation, and form 2 at the top. We were getting form 1. So it looks like what we may have been doing is getting the suppression of crystallization into that little wedge again, and increasing the supersaturation beyond which they can do through just solvent-mediated means. We're suppressing the crystallization, increasing the supersaturation, and making form 1. This is just a flow chart of how we've been getting the different forms of carbamazepine. This is now 2 systems in which we've seen it work. A difference in the carbamazepine unit cells, form 1, form 3. This again was work by UCL. Form 3 has this inversion cup motif, which goes through the crystal, and all of the hydrogen bonds point in the same direction, which is kind of interesting. Form 1 has these kind of offset stacks. Is that significant? Well, the susceptibility calculations would suggest that the form we get out of the magnet has a higher magnetic susceptibility than that grown in the magnet. I mean, make of that what you will. It looks like the magnetic anisotropy of the unit cell may not be an important factor when growing these crystals. Just a quick note on charge transfer complexes and why polymorphism is important in these systems. Charge transfer complexes in organic crystals are very important. They've been superconductors if you pick the right combination of donor and acceptor in these co-crystals. And specifically, we have here stoichiometry of 1-to-1 in these co-crystals. Now, technically, you can change the polymorph of these co-crystals also, and drastically change the charge transfer properties. So a mixed stack, which basically has this alternating molecules in each stack, has typically a lower conductivity than the segregated stack, donor and acceptor. So if we can take something that grows in a mixed stack and make it a segregated stack, possibly using magnetic fields, then we can increase the charge transfer properties of these crystals. So effectively, just to kind of summarize where I think the mechanism of this lies, because we're still not at the bottom of it, is we dissolve material up to a saturation point. and then we remove any nucleation sites that we can. So we filter with the smallest filter we can, keeping the temperature elevated. Then we make it sealed and we start to cool. So we get this supersaturation again, but we're able to push the supersaturation further and further down the temperature gradient. So it has a greater supersaturation than this, okay, which is important because it's probably where the selectivity of the polymorphism lies. So we get form A at lower supersaturations, form B at higher supersaturations, and the magnetic field is allowing us to access these higher supersaturations. So to summarize that, all properties associated with a bulk molecular crystal are a function of the interactions between molecules. You change those interactions, you turn a molecule over, things change. Any property can be affected by this. Another thing that's important is that if you're doing an experiment and you're growing a crystal in situ, in a microscope, in a magnetometer, in an NMR machine, sometimes there is an intrinsic field present. So if you're growing a crystal with an intrinsic field present, you have to take that into account. You can't assume that the crystal you want has grown because there's a magnetic field present. So if you want the orthorhombic form of rubrene grown in a capillary at the bottom of a squid magnetometer, you can't assume that it's the orthorhombic form that's grown because the field could be making a difference in changing the polymorph. It seems that there's preferential growth of the metastable polymorphs under field, and suppression of crystallization being observed. Looks like we're getting these metastable forms because we're pushing the supersaturation that far, and that magnetic fields might be a means of reaching these supersaturations that have yet been unattainable by other means. Just things that we're looking into at the moment. We've got a liquid cell over at Limerick, a liquid cell sample holder for a transition electron microscope, which is very exciting. So we can watch these crystals growing. We also have NTA, which is nanoparticle tracking analysis, which and identifying and characterizing model systems based on the interactions involved. So we know that the field is having an effect in these samples nucleating. What we need to know is why are they having an effect. So instead of just growing crystals, maybe we're going to try putting things in which exemplify a particular type of interaction. So something that's massively hydrogen bonded. If we put that into the system and it won't grow, does that mean the magnetic field is suppressing hydrogen bonding? If we've got something that exclusively pi stacks and it doesn't grow, does it mean the magnetic field is suppressing pi stacking in the system? But we're going to get to the bottom of it. I've got a year left of my postdoc to do so. Just to thank some people that have helped me quite a lot. My group, Simon, Charlie, Vicky and Nicole back in Bristol, have been invaluable with getting the lab set up and getting sample preparation done. UCL, Rui is the guy that did all the calculations. He's an absolute wizard with it. These are the guys from Radboud that have the high field magnets. Limerick, we have Jen who's working on the TEM. Liana and Gabrielle helped a lot with identification of the crystal characterization of beta coronine. The rest of the group back in Bristol, Simon, Ed and Richard who helped me put the magnets in place, the EU for the funding, and Kamal Sensei and Keio for inviting me over to give this talk, and this is my group here. Is that good time-wise? Yeah? Okay, well then, thank you very much for listening.
Thank you, Jason. I hope to do a question and answer for his very good. Excellent presentations. Any questions from undergraduate student or PhD candidate or professor?
Thank you for your presentation, and I want to know that if you want to control the polymorphism form, and the electromagnetism is the static or dynamic control is more effective for control the polymorphism?
We haven't really established that kind of control with our own methods just yet.
Okay.
The problem is crystal growth is so stochastic and seemingly random. You can do things 100 times and it works, and then time 101, it does something completely different. So it's all about running the statistics. So you have to do lots of experiments each time. By adding another variable, which we're trying to cut out, it just increases the parameter space in a completely different dimension, and just makes the amount of work that we need to do impractical. But you're right; it's a very good question.
So to control the polymorphism, we have to think about a lot of parameters to control the polymorphism.
Well, yeah, like I said, a lot of people that work in crystal growth and outside of crystal growth think that it's almost magic. Some crystallographers have been able to grow things for years that no one else can grow. So what I'm basically saying is any parameter, any variable, seemingly can change the polymorph. It's about getting a handle and being able to do it reliably and often. So the more things we bring to the table, the more options we have. So for instance, in the past where you could have a particular polymorph appear and then suddenly it disappeared and no one can grow it again. Maybe they were growing crystals near an NMR machine and there was a slight magnetic field on it and that was changing the polymorph. Then they moved benches and suddenly they can't grow it anymore. It's a massive pain, but
Okay, thank you very much.
Well, how did you calculate the free energy in the did you use the package?
well, that was all done at UCL by Rui. So I couldn't give you the explicit calculation that he used, but what I know that he uses a package called CASTEP.
CASTEP?
Yeah, CASTEP. And with solid state calculations, he tends to stay with PBEO for functional, and I think 6311 as a basis set. So I wouldn't be able to do it myself, but I know enough to sort of hand wave my way around the calculations.
Thank you.
I have several questions. What does it mean? I use demonstrate the calculation result using DFTD. Density functional theory. What does the mean of D?
Dispersion corrected. So a lot of DFT calculations don't take into account dispersion forces. So pi stacking. So if you just use standard DFT functionals, you put the two molecules together, they just drift apart. If you have dispersion corrected DFT, then it takes into account the dispersion forces, and they're attractive and they lock together. So that's what the D means with DFTD.
Yeah, your group do the DFTD using a CASTEP?
We do DFTD using Gaussian.
Gaussian.
Yeah, which is just for small numbers of molecules.
Okay.
I think you need under 55 atoms, but small
size.
Small, yeah. CASTEPs for big crystal repeating structures. Yeah.
Thank you very much. And the last slide, you you showed us the supersaturation and it is and hysteresis of the amount of dissolution. Okay. Greater temperatures. This point depends on the magnetic field. Or other.
It can do. So, sorry. It can do. So, the goal with the supersaturation is to get it as far down this line as possible. Now, it could get to here and then crystallize. It could get to here and then crystallize. But this can be affected by the purity of your solvent, if you're using an anti-solvent, the speed in which you cool it down, the speed in which the solvent's allowed to evaporate. Using a magnetic field with all other things the same should looks like it's pushing this just a little further and allowing us to get forms that maybe we couldn't access otherwise. So yes, maybe the higher field is pushing it further this way, but it could be other factors that do it as well.
Thank you very much. Any other question? Okay. Now, thanks again, Dr. Potticary.